Hello and welcome to lecture 15 of the course Theory of Computation. In lecture 14, we stated Myhill-Nerode Theorem, which was a necessary and sufficient condition to show that languages being regular. We set up definitions and then we stated the theorem. Right? The theorem states that a language L is regular if and only if it has a finite index, and also this index is also the size of the smallest DFA that recognizes that language, right? If it is finite, of course. The proof, we said that it boils down into two lemmas, basically either direction of the implication of the proof. We quickly saw how these two lemmas imply the theorem, which was fairly straightforward, right? And now what remains is to show these lemmas. Right? So now let us proceed to the proofs of the lemmas 1 and 2. Right? So before stating the lemmas, I'll just set up a brief notation. So we have the definition of the transition function, right? So we have the definition of the transition function delta QA, which is the where, like, so suppose this is equal to R. This means that from state Q, if you see the symbol A, you reach state R, right? If you see the symbol A, where A is a symbol of the alphabet. Now here I am defining sort of a shorthand notation, delta star QX. It's exactly like this, but instead of a symbol from the alphabet, I am defining it for a string, right? Not a symbol. So for instance, X could be AB, right? So suppose now if you read AB, you get to state S. So if you read AB from Q, you go to R and then go to S. So then you will say delta star Q comma AB is equal to S. So the delta star means that the number of steps, or that could be more than one, right? Then, or the length of the string is equal to the number of steps in a DFA. It could be more than one, right? So when you start from Q and read the string, where do you end up? This is delta star, right? So this will be used in our proof. So that's why I am stating this notation up front. So what is lemma 1? Lemma 1 says that if L is recognized by a DFA with k states, then the index is at most k. Okay. So let's see. So what is index? Index is the number of equivalence classes. Another way to see it is the size of the largest pairwise distinguishable set. Right. Okay. So what we will do is that suppose L has a DFA with k states. We will show that any two strings that end in the same state are indistinguishable. So suppose there are k states. So now we are saying that anything that end in the same state, any string that ends in the same state is indistinguishable. So suppose there are infinite strings that end in a certain state, all of them are indistinguishable, meaning from the strings that end in that state, I can only pick one string in the pairwise distinguishable set, right? So let's see. So suppose L is recognized by a DFA M with k states, okay? And suppose for the sake of contradiction, the index is more than k, okay? For the sake of contradiction, index is more than k, right? Now we'll show a contradiction to this assumption, right? This means that there is a set X that is of size more than k, right? That's what index means. There is a set X that is of size bigger than k, which is pairwise distinguishable, meaning any two that you take from X will be distinguishable by the language, right? Now let Q0 be the starting state of the DFA. So we assume there is a DFA, right? And k is the number of states. Now you take each of these strings from X, right? Suppose X has, let's say k is 10 and suppose X has 11 strings. For each of these strings in X, you see where the DFA ends after reading them, right? you see where the DFA ends after reading them. There are 11 strings and there are only 10 states. So at least 2 of these strings must end in the same state. Right? Same thing I am saying here. By pigeonhole principle, there exists 2 strings, 2 distinct strings in X, capital X, right? There exists 2 distinct strings in capital X, X and Y, small x and small y, distinct. So X is not equal to Y, such that they end in the same state, right? So X and Y end in the same state. This of course will happen because there are more than k strings in capital X and there are only k states. So at least 2 of them should kind of coincide as to where they end, right? So now X and Y end in the same state. Now by assumption, small x and small y are pairwise, are distinguishable by the language, but now we will contradict that by showing that they are actually indistinguishable by the language. So now as far as the DFA is concerned, both of them ended in the same state, right? That's right. Now whatever z you append to the x or to the y, now we will show that wherever the DFA goes with when it sees xz, let's say where it goes, right? For any z in sigma star, where does the DFA end? That is exactly what is given by the notation here, delta star q0 xz. This is the state where xz ends up being, right? So another way to see this is, you first see where x takes q0, sorry, x takes the DFA, followed by where does z take from there, right? So suppose x takes it to, suppose this is equal to the state R, x takes it to R and then also y takes it to R, right? So maybe, so this is same saying, now from R where does z take it to, right? But what is R? R is also delta star q0y, right? And this is nothing but where does the DFA end up when it sees yz, right? So what it means is that starting from the starting state, xz takes it to some state. Let's say it takes it to the state, let's say t, or let's say that state t. Yz also goes to the same state t. Meaning, if t is an accepting state, both xz and yz are accepted. If t is not an accepting state, neither xz is accepted nor yz is accepted. So either both of them are in L or neither of them are in L. So that's what I have written here. So xz being in L if and only if yz is in L. Right? If xz is in L, yz is in L. If xz is not in L, yz is not in L. That's what I have written here. It's if and only if. So which means that whatever z you put at the end of x and y, it is not going to distinguish, because as far as the DFA is concerned, where did x take you, where did x take the DFA to, and where did y take the DFA to, that's all that matters. Now from there it sees the same string z, so it follows the same trajectory and in the same state. But we know that x and y took it to the same state R, right? Hence they are indistinguishable. This means x is, so not pairwise indistinguishable, that's an error. So x and y are indistinguishable, so I should say by L, right? That's what the definition was. X and y are distinguishable by L. I'm sorry. I just erase it and write. No, not distinguishable, indistinguishable. because whatever z you put, it is not going to distinguish them, right. So this is a contradiction, because X was supposed to be, capital X was supposed to be a pairwise distinguishable set, but here we are two distinct members of capital X which are indistinguishable. So that's a contradiction. So the assumption that it contradicts was that index of L was strictly greater than K. Hence the assumption is wrong, and hence the index is less than or equal to K. So we showed that if L has a DFA with K states, the index is at most K, which is the statement of lemma 1. Right. So the next statement or next lemma that we have to show is lemma 2, which is opposite. So we showed that if there is a DFA that recognizes L with K states, in lemma 1 we said that if there is a DFA that recognizes L with K states, then index is at most K. In lemma 2 we say the opposite. If index is at most K or index is equal to K, then there is a DFA with K states that recognizes L. Right. So if the index is 10, then we can construct a DFA with 10 states. Right. So what we do here is we actually construct a DFA of using the index. So suppose the index is K, which is a finite number, right. Now we are going to construct a DFA. So let capital X be equal to x1, x2 up to xk, be a set of pairwise distinguishable strings, right. So this is the largest set of pairwise distinguishable strings, right. So that is the definition of index, right. Index is the size of the largest pairwise distinguishable set X by L, right. So index is K, so we can make a set of size K, which is x1, x2 up to xk, right. Suppose these, so now what we will do is we will use this set X to construct the DFA. So let us construct the DFA. So let M be the DFA with Q, sigma, delta, Q0 and F. So sigma is already, we know what it is, and Q is the set of states, and the set of states are going to be Q1, Q2 up to Qk. Okay, there are going to be K states, which is what we want to show, right. If index is K, there is a DFA with K states. Now Q1 to Qk, each of these states, so Q1 will correspond to with x1, right. So Q1 here will correspond to x1, Q2 will correspond to x2, and so on. Qk corresponds to xk. So each Qi corresponds to the respective xi. Let us see how in a moment. So now the next thing we need to define is how are the arrows defined, right. So let us take Qi and then it sees a symbol A, where do you end up, right. So this is the question, right. So this transition needs to be defined. So notice this, that Qi corresponds to xi. So let us take xi. Now let us append A to xi. So xi is some string, you append it, you get a bigger string. Now this string xia, this string xia, which is I am underlining over here, it is equivalent to some other string in capital X. So capital X is the largest set of strings that are pairwise distinguishable. Okay. So xia will be equivalent to some symbol, some string in that set X, because if it is not equivalent to some string in that set, then you can add xia to the set and get a bigger pairwise distinguishable set. But then that is not possible, because we assumed, or by definition, this is the biggest pairwise distinguishable set. Okay. So xia must be equivalent to some string in capital X. Let that string be xj. Okay. So let that string be xj. So now xia is equivalent to or is indistinguishable with some string in capital X. Now that string, let us say it is xj, Now what we do is, now we ask the question, where does this arrow go to from Qi upon reading symbol A? The answer is it goes to Qj. How did we get Qj? We saw what is equivalent to Xi followed by A. Right? That is how we get the transitions. So now for all the states Q1 to Qk and for all the symbols in the alphabet A, B, C, whatever, 0, 1, whatever be the alphabet, we do this to find out where does the arrow point to, right. So that gives you the transition. So I have defined the states Q, I have defined the transitions delta, sigma is already known. Now what remains to be shown is defined is the starting state Q0 and the accepting states F. Just like I said before, the empty string epsilon is equivalent or is indistinguishable from some string in the set X, right. The empty string epsilon is equivalent to some string in the set X. Let us call that string Xm. Why does it have to be equivalent? Because if it is not equivalent, it is distinguishable from all the other strings in X. You can add the empty string to X and get a bigger pairwise distinguishable set, which is not possible. So empty string better be equivalent to some string already there. Equivalent meaning indistinguishable with some string that is already there in X. And suppose it is Xm, right. So suppose empty string is equivalent to Xm, then the corresponding state Qm is to be set as the starting state. So empty string will be equivalent to some string Xm, and the corresponding state is the starting state of the DFA. Finally, the last thing that needs to be defined. So we have defined set of states, alphabet is already known, transition is known, starting state is defined. The only thing left is the accepting states. Accepting states is fairly straightforward. We have x1 to xk strings and correspondingly we have q1 to qk states. Some of these x1 to xk are in the language L, right. Suppose x1 is in L, if x1 is in L, then you make q1 an accepting state. If x2 is not in L, you make q2 not an accepting state. If x3 is not in L, you make q3 not an accepting state. If xk is in L, you make qk an accepting state. So whichever xi is in the language, that qi will be an accepting state. Whichever xi is not in the language, that qi is not in the accepting states. Now all that we need to do is, we have defined the DFA, right. We have told what is q, what is delta, what is sigma, what is q0, what is f. All that we need to do is to show that this DFA recognizes our language. So we will first state this following claim, which is kind of what we are building towards. The claim is that suppose upon reading the string w from from qi, suppose reading the string w from the state qi, right, you move to qj. So delta star of qi w is qj, right. When you meaning, so you are in qi and then you read, so I am reading squiggly lines because it may not be one transition, it could be multiple transitions, and then you get to qj. Okay. This means that if this happens if and only if xiw is equivalent to xj. So these two things are equivalent, or these two things happen together or do not happen together, right. If one of them happens, the other one also happens. So first let us complete the proof that, see, what do we want to do now? We assume that by assumption the index is k. We wanted to show that there is a DFA with k states. We actually constructed a DFA with k states. We want to show that this DFA recognizes the language L. So what we will do now is to assume that this claim is true, right. So we will assume that this claim is true. Okay, we will assume that this claim is true, and then we will prove that this DFA recognizes L. After which we will prove the claim. The claim is fairly straightforward, fairly inductive, standard inductive proof. Okay. So let us just forget the proof of the claim for a moment, and we will prove that the DFA constructed recognizes the language. Let us see how. So how do we show that the DFA recognizes language? We will show that every string in the language is accepted and every string is not in the language is not accepted. Okay. So suppose X is in the language, right? Suppose X is in the language, and then it follows that it is equivalent to some string that is in the language, right? Not only it is equivalent to some string that is in the set X, right? Because X is equivalent to some string in the language and some string in the set X, because X is the largest pairwise distinguishable set, and whatever it is equivalent with will have to be a string in the language, right? So X is equivalent to some Xi that is both in X as well as in the language, right? Which means that so now X can be viewed as empty string followed by X, and we know that this is equivalent to Xi, right? So empty string X is equivalent to Xi, which means by the claim that we just said, this means that delta Xi empty string followed by X is equivalent to Xi. This means that delta star Q0 X is equal to Qi, because Q0 is a state corresponding to epsilon, the empty string, right? That's how we constructed. X is the same. Qi is a state corresponding to Xi, right? So delta star Q0 X is equal to Qi, meaning from the starting state, upon reading the symbol X or upon reading the string X, the machine ends at, or the DFA ends at Qi, right? And by the definition of the accepting states F, right? So what were the accepting states? All the Xi that were in the language corresponds to all the Qi that are accepting states. So since by assumption Xi is a string in the language, Qi is in the language. Therefore, upon reading the string X, the DFA ends at Qi, and which is an accepting state. So X is accepted. So then the next part is fairly similar, right? We have to show that any string that is not in the language is rejected. So suppose X is not in L, this means X is equivalent to some Xj that is in X, right? X is equivalent to some Xj that is in X. This Xj must be in X, but is not a member of the language, right? Because otherwise they will not be equivalent. Similar to above, we can do the exact same thing. X is equal to empty string X, etc. We will get that using the claim. You get the delta star Q0 X is equal to Qj, meaning upon reading the string X from the starting state, the DFA ends at Qj. And exactly like before, since Xj is not in the language, Qj is not in an accepting state, right? Qj is not an accepting state, which means the string X takes the DFA to a state Qj, which is not an accepting state, and hence it means that the DFA does not accept the string X. So we considered an X that is not in the language. We showed that M does not accept the string. So whenever X is in the language, M accepts. Whenever X is not in the language, M does not accept. This means that M recognizes the language, right? So fairly straightforward proofs once we assume the claim, right? The claim is also sort of technical. So let me just recap it very quickly, the lemma so far, before moving to the proof of the claim. The lemma statement is that if the index is equal to k, there is a DFA with k states that recognizes the language. The proof is constructive. We actually constructed DFA with k states, right? So the index is k means that there is a set of k pairwise distinguishable strings we make a DFA where each state corresponds to each of these case strings, and we define the transitions, accept state, start state, everything correspondingly. Start state is the state that corresponds to the string equivalent to the empty string. Accept states are the states that correspond to the strings that are in the language, and then we use that to show that any string in the language X are accepted and any string that are not in the language are not accepted. And what remains to be shown is the following claim. Right. The claim is that, I'll just copy it from here. The claim is something like this, right? So suppose the string W takes the DFA from Qi to Qj, then XiW is equivalent to Xj, right? And vice versa. If XiW is equivalent to Xj, then W takes the string from Qi to Qj. And this is fairly straightforward. This is done by induction on the length of W. So the base cases are simple. So I'll do two base cases, 0 and 1. The base cases are the induction is on the length of W. So the first base case is when W, the length of W is 0. There is only one string that is of 0 length, which is the empty string. So what is delta star of Qi empty string? Meaning, where does empty string take the DFA from Qi? It takes it to itself. And trivially, Xi epsilon is equal to Xi. Right? This is what we have to show. If empty string takes it to some other state, then Xi epsilon also is equivalent to the corresponding state. So empty string takes it to Qi, right? Because empty string cannot move the states in a DFA. But then Xi followed by empty string is equivalent to Xi itself. So hence this is true in the case of W equal to empty string. When W equal to 1, which means the length of the string is 1, which means W is a symbol from the alphabet, right? W is some symbol A from the alphabet. Now delta star of Qia, meaning where does A take the DFA starting from Qi, right? This is just a transition function because it's a single symbol, it's not a string, it's a single symbol. So it is the same as delta of Qia because we can remove the star. Delta of Qia is equal to Qj. If you remember, the way we define delta Qia equal to Qj, right, was by checking what is the equivalence of Xia, right? So what is Xia equivalent to? We set it to be Qj because Xia was equivalent to Xj. So by the definition of the transition function, Xia is equivalent to Xj. So the claim is true here as well. So this is just by the definition of the transition function. Now the main thing is the induction. So we showed it for the length equal to 0, length equal to 1. Now the next thing is the induction step. Suppose W is of length greater than 1, and let's say W is of the form VA, right, where V is a string and A is a symbol. Okay. So length of W is length of V plus 1. So V could be some string. Right? Length of V is L minus 1. Right? And A is a single symbol from the alphabet. Right? A is a symbol from the alphabet. And so where does W take the DFA starting from Qi? So first we will see where does V take the DFA, right? Where does V take the DFA? And then we will see where does A take the DFA. So we can break down W as V and followed by A. Suppose V takes the DFA to Qji, right? Sorry, Qj1, and then A takes it to Qj2. Okay. So Qj1, as I said before, is where does V take the DFA to, and Qj2 is where A takes from Qj1. By induction, right, so Qj1 is delta star Qiv. By induction, it follows that xj1 is equivalent to xiv, and by definition of delta we have xj2 is equivalent to xj1a, right, because by the definition of delta, because delta qj1a is qj2, right. So now xj2 is equivalent to xj1a, right, by whatever I have written here, right. So this follows by maybe what I have written here, the first equivalence, and the second equivalence is that xj1 is equivalent to xiv, right. So maybe I'll mark it green color, and this is the green equivalence. xj1 is equivalent to xiv, but then xiva is simply xi is as it is and va is the same as w. So this is maybe I'll use another color, this is red color, this is equivalent to, or this is equal to xiw, not equivalence, right. So now we have shown that xj2 is equivalent to xiw, where qj2 was a state reached from qi, starting at qi upon reading the string w. So which is what we wanted to show. We wanted to show that if the DFA goes to qj starting from qi by reading the string w, then xiw is equivalent to xj. So here the state that it went to was qj2, and here we are saying that xiw is equivalent to xj2. So this means the claim holds for in the inductive step as well, right, and that completes the proof. So my if you find the induction too technical, my suggestion is to probably forget the induction for a moment and just try to understand the rest of the proof. The rest of the proof is fairly nice and easy to follow. Try to just believe the claim. Forget about worrying about the proof of the claim. Try to believe this claim that is in the red box, and try to see how the construction of the DFA works. The construction mainly works by, for each string that is a in the pairwise distinguishable set capital X, we make a state and we make the transitions accordingly, and that somehow magically works together, right. It's not magical, but it's somewhat sensible as well. So try to follow this proof without worrying about the proof of this claim, right. And once you understand that proof, then you come to the then you can come to the understanding the proof of the claim, right. So the proof of the claim is also fairly standard, but try to separate the two so that if together it becomes too hard to follow. That's one suggestion, right. And so what we showed is the proof of lemma 1 and lemma 2. So lemma 1 said that if L is recognized by a DFA with k states, then the index is at most k, right. This was shown by assuming assuming that this is not the case, and then by showing a contradiction. If the index was greater than k, then we showed that two strings from the pairwise distinguishable set must end at the same state, and then we said that anything that ends at the same state must be pairwise indistinguishable, which contradicts what we said earlier. Then we said lemma 2 said that if the index is k, then there is a DFA with k states, which we proved in a constructive fashion, and that together imply the Myhill-Nerode theorem. Finally, just a brief example. In fact, part of this example we touched upon in the lecture 14. So consider the language is 0 power n, 1 power n. Okay, this is the language. So this, as we saw in I think lecture 13, this is the empty string 0, empty string 0 1, 0 0 1 1, and so on. And so on, and this is, we know this is not a regular language, right. And let's see why Myhill-Nerode theorem implies that this is not a regular language. So basically we will try to to show that it's not a regular language, we need to show that the index is not finite. So consider this following set X. Okay, so X consists of all xi. So maybe I'll just rewrite xi. So maybe I'll just rewrite it here. X is basically 0 power I for all I. So it's just the string 0, empty string followed by 0, then 0 0, then 0 0 0, and so on. Right? This is an infinite set. The claim is that this is a pairwise distinguishable set. Right? So why is it a pairwise distinguishable set? So we kind of saw the proof already in lecture 14. So consider these 4 strings 0 0 0 0 0 0 0 0 0 0. So anything, if you consider if you try to append 1, 0 1 is in the language, but 0 0 1 is not in the language, 0 0 0 1 is not in the language, and 0 0 0 0 1 is also not in the language. So the first string 0 is distinguishable by from any other string in the set. And similarly, if you consider 1 1, appending 1 1, so 0 1 1 0 1 1 is not in the language, but 0 0 1 1 is in the language. Hence the second string 0 0 is pairwise distinguishable from all the other strings. So it's the same argument again. So if you see this set X here, right, it's an infinite set. It contains empty string 0 0 0 0 0 0 and so on. The string 1 power I will ensure that just xi alone is in the language. Xi 1 power I will be in the language, but xj 1 power I will not be in the language for whenever j is not equal to, when I is not equal to j. Right, xj 1 power I is not in the language. Hence 1 power I distinguishes xi and xj. Like that. So if you take any xi and xj, the 1 power I will distinguish them. Hence all the strings in the set capital X are pairwise distinguishable. Hence this is an infinite set that is pairwise distinguishable, which means the index of the language A is infinite, and that kind of is consistent with what we know, which is that A is not a regular language. So the index is infinite, hence A is not regular. Right, so this is something that we have already seen in said in lecture 14. Anyway, so this concludes the part on Myhill-Nerode theorem, which is a necessary and sufficient condition to show that a language is regular. Right, this is a necessary and sufficient condition. So we defined this equivalence relation, and the condition is that A is regular if and only if the equivalence relation defined by A results in a finite number of equivalence classes. And with that, we come to the end of the part on regular languages. Right? This is the last topic in the section of in the first chapter, which is the chapter on regular languages. In fact, this part, this Myhill-Nerode theorem is in fact not there in the textbook per se. It is listed as an exercise, but this completes the part on regular languages. So the next thing that we will see is context-free languages, which are slightly more sophisticated or more intricate or more involved than regular languages. Right? So regular languages are fairly simple, regular expressions and DFAs and NFAs. Context-free languages involve another dimension. There is more things that you can do with context-free languages. So we will see that in the next lecture.